Now that we've written ways to write the equation for an explicit rule and for recursive rules for arithmetic and for geometric, now we're going to back up to something called arithmetic series. And arithmetic series means we want to add up the terms of a sequence. So maybe we have, for instance, we have the numbers 2, 8, I'm adding on 6, 14, adding on 6, 20, and so on. And this is an arithmetic sequence. And if I ask you to add up the first, say, 40 terms, here's the 40th term, add up the first 40 terms of an arithmetic sequence, that's called adding up an arithmetic series. So a series is just the sum of the terms of a sequence. And so we'll go back and look at where this problem or the formula for this actually came about, and from a very, very wise young child named Carl Friedrich Gauss. And you can see when his lifespan was, so it was many, many years ago. And the story goes like so, that he was posed as like an 8-year-old this question to add up the integers from 1 to 100. And the interesting thing is how he did it. And what he did, and he did this all in his head. He did not write this down. The only thing he wrote down was what the answer was, as the way the story goes. But he said, I want to add up the terms from 1 to 100. So he thought about what would happen when he added them up. This would be called a series, S sub 100, meaning I'm summing up 100 numbers. And normal people would go 1 plus 2 is 3, plus 3 is 6, add on 4, we're up to 10, and so on, and just continue to add them on. But he thought, I wonder what happens if you rewrite or think about the series backwards. And so 100 plus 99 plus 98 plus 97, all the way down to 2 plus 1. And he knew that the sum of these numbers would be the same as the sum of these numbers. It doesn't matter which order you add them in. And so he looked at if you added these down, position them above each other, the sum of these first two numbers add up to 101, the second number is 101, third number is 101, last number is 101, and he finds that you really, if you sum up two series of 100 numbers, it's really 100 ones added together. So he said there are 100 ones added together, and that's two series. And so when he divided that by 2, he would end up getting the correct answer, 5,050. Now, interestingly enough, you can actually do that. That's the sum of the terms of this arithmetic sequence is a series, this arithmetic series. And interestingly enough, it will work with any type of sequence that's arithmetic. If I take 2 plus, what did I have before? Well, I'll just do this. 2 plus 8, adding on 6, plus 14, adding on 6, 20, adding on 6, 26. Now, that's the sum of 1, 2, 3, 4, 5 numbers. I could just add them up. But notice what happens if I put them in reverse order. 26 plus 20 plus 14 plus 8 plus 2. When I add them down, every time all of these numbers will add up to 28. And so that would be two series of 5s. So I would be taking 5 times 28 and dividing it by 2, and that would tell me what the sum of those 5 numbers was, so whatever 14 times 5 is. But in essence, think what happened. This is really the first number, the 28, is the first number plus the last number. And then it was multiplied by how many numbers you were going to have by 2. And he saw that that pattern worked all the time. I don't know if he proved it mathematically, but he found the pattern, and he's credited with it. So we have the following, that if we have an arithmetic series, which means we want to find the terms of an arithmetic sequence, like so, we take the first number, the last number, first plus last, and then multiply it by how many terms you're adding up over 2. Now, sometimes we don't know this last number, and we actually have to figure it out. For instance, if I were up here and I said, hey, let's add up the first 40 terms, well, the first thing I would have had to have done is figure out what this number was. And I would have figured that out by saying, all right, the 40th number is 2 plus, I kept adding on 6 each time, and I would have done that 39 times to get to the 40th term. So for me, to add up the first 40 terms, I would have taken first plus last, which would be this number. That's the last number, the 40th number, times how many terms over 2. And that would have added up all 40 of those numbers just in a snap. So I have another little rule for this, that here's the first number plus, just like I said, sometimes you have to calculate the last number in the arithmetic series, times n over 2. Kind of turn that the right way. Now, we also are going to be looking at sigma notation, and let's look at the way we write that out. We're going to have an explicit rule here for generating the term. So there's our explicit rule for generating the sequence. It actually does not have to necessarily be arithmetic, but in our case that's what we'll have. So we have a way of generating the terms of the sequence, and the sigma notation, the capital S in Greek letters, is signified, and we will have whatever letter we're using for our rule in here. I'm using n, and so we're going to let n start as 1, and then we'll go up to however high we're going. If this says 40, then this last number would be 40. So this would not end up being an n or a variable in the end. It would end up being whatever this number was that we wanted to end up having. This is our last sum. So we'll look at a couple examples down here and write some sigma notation. Okay, so we have, here is a finite sequence. It's just a listing of some terms. Finite meaning it stops, it doesn't continue on. Here's a finite series. I'm now adding these terms together, so that's why it's called a series rather than a sequence. Here's an infinite sequence because I put the dot, 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 meaning the pattern continues to go on forever. Here's an infinite series. I'm adding the terms up of an infinite sequence. Therefore, it's called an infinite series. Now, our summation notation, or sigma notation, we can look at here, and you can see on your sheet that if I look at this, we have an explicit formula for our sequence right here. This variable n is going to match with what this lower index will start with, and we always, for almost everything we do, we would start with n being 1. I will show you some examples of where it doesn't, but normally when we write it in sigma notation, we usually start it with 1. And this would be the last number that would be added in. So if I had this series, the sigma is telling me you're going to add up. This lower one says plug 1 in to begin with. And when I do, I get 5 plus 1. I would get 6. And then plus, that's what the sigma means. Next number, you always increase by 1. And my next number would be to plug in 2. So I would get 11. Plus, my next number is to plug in 3, and that would be my last number I'll plug in. Plug 3 in here, 15 plus 1, so it's 16. So this is literally asking me to find 6 plus 11 plus 16. Now notice this is arithmetic because it's going up by 5 each time. Now let's flip over, go through a couple more things. May not do all of this on one video, but we might. So starting out here, we want to write the related series. So a sequence is just a listing of terms. Notice it is arithmetic. We're going up by 4 each time. So here's the related series. We want to find the sum. Well, we could add them up. There are 1, 2, 3, 4, 5, 6, 7 numbers. But if it's arithmetic, it's really nice to add up. First plus last times n over 2. First plus last times n over 2. First plus last times n over 2. And so that will add up to 119. Now if I'm going to write it in sigma notation, remember I'll have my sigma. I'll start with n being 1. I'm going to be adding up 7 terms. Now I need the explicit rule for generating this sequence of numbers. And then we know we start with 5, and we keep adding on 4, and we would do that n minus 1 times. And that will generate the sum of those 7 numbers. So that's my sigma notation for writing it out. We could also simplify this rule, which I did right here. So not too hard. Now, here are a couple of examples of looking at just like a geometric example where we're having a series. So a staircase uses same size cement blocks arranged 4 across as shown. Find the total number of blocks in the staircase, and notice that if I look at the pattern, that this top row has 4 blocks. Then the next row is going to have 4 and 4, it's going to have 8. The next is going to have 4, 4, 4, it's going to have 12. Every time I increase and I have another 4 blocks on a row. So here's my top row, second row, third row, and so on. And I have 1, 2, 3, 4, 5 rows. So those are the things I need to add up. Now it's easy enough just to add up those 5 numbers. However, I could do first plus last times n over 2 to add them up quickly, particularly if there are a lot more rows. If the pattern continues, how many total blocks will there be in 10 rows? Well, now I don't want to add up all 10 rows. I definitely want to use this first plus last times n over 2. And when I do, I have to find how many would be in that bottom stack of rows. So I have first plus last times 10 over 2. And here I'm finding my 10th position, my 10th row, which I wrote the explicit rule. Start with 4, add on the common difference, n minus 1 times. So there actually will be 40 blocks in that bottom row. First plus last times n over 2. Number 3, going to find sigma notation for this series. And I want to write sigma notation for the sum of the first 50 terms. So I need to know an explicit rule. So I start with 8. And I'm adding on 8 each time. I would do that n minus 1 times. Oh, and look, it's just 8n. Silly me. I can see that 8 times 1, 8 times 2, 8 times 3. So if I want to write sigma notation, I need to write my sigma. I need to have what my explicit rule is to generate the terms of the sequence. Let n start at 1. And I'm going to add up until I finally get to 50. And look how slick this is to add up 50 terms very quickly. First plus last, when I plug in 50, times n over 2. Very nice, very efficient. Find the sum of the following series. Now here's the little catch here. Notice here I don't have this starting at 1. I have it starting with 3, so it doesn't have to start with 1. When I plug 3 in here, I get negative 6 plus 3, I get negative 3. My next number to plug in would be 4. The next number is 5, 6, 7, 8, 9. And notice there are only 1, 2, 3, 4, 5, 6, 7 terms. The key thing you have to remember is, look up here, 50 minus 1 is 49, but there are 50 terms. 1 to 50 is 50 numbers. Just like here, you got to watch out. 9 minus 3 is 6, plus 1, there really are 7 terms. So if I do first plus last times n over 2, I have to remember that there are 7 terms there. And so this number doesn't have to start at 1. We have to be careful about figuring out how many numbers there are, though. It's not this value that's going to plop here. It's however many numbers there are from 3 up to 9. All right, close to the end. Look how quickly we can add up 450 numbers. Plug in 1, plug in 2. I'm establishing that I have an arithmetic pattern, and I do. I keep adding on 2 each time. Now I'm going to find that 450th number. Plug 450 in there. 900 minus 6 gives me that 894. Isn't this cool? First plus last times n over 2. We just added up 450 numbers. Now here's an example of a geometric question in which we want to find how long to cut some different strips. And I have 15 feet or 180 inches of ribbon. And I want to cut 8 strips, and I want them each to be 6 inches longer than the previous one. So, and then I'm going to put them on a banner. So we have one, and then another one's going to be like this, and another one's going to be like this. And I want this to be a 6-inch difference between. And so here's the first ribbon, here's the second ribbon, the third ribbon, and we would go all the way out to have whatever this 8th ribbon is. And I know that when I add these ribbons up, I want them to add up to exactly 180 inches. My problem is I do know what the difference is between, but I don't know how long to cut the first one. Once I know how long to cut the first one, the second one will just be 6 inches longer, the third one will be 6 inches longer than that, and so on. So I don't know how long to cut my first one, but I know my second one will be whatever the first one was plus 6. The third one is going to be 6 inches longer than that one. Now I'm generalizing. The 8th one will be the first one plus the common difference times n minus 1. So in reality, this last ribbon is going to be 42 inches longer than my first one. So first plus last times n over 2 has to add up to this. And I did my algebra, and I find out the first one's only going to be 1.5 inches long. Last one would be 43.6, and they will be perfectly cut to each be 6 inches longer than the next one. Last two examples, just showing you some different ways that the questions can come up. Now I want to find the sum of these numbers. I can see it's arithmetic. You keep adding on 4 each time. My problem is I don't know how many are adding on. I know first plus last times n over 2, and in this case, I actually have to figure out what position this is. So 373 you get by taking 5 and adding on 4 n minus 1 times. I did the algebra and found out that this is really the 93rd term. So now I can do first plus last times n over 2. As opposed to a little bit different question, but somewhat similar, now I know that I have these numbers, and I want to continue adding these numbers up until I finally get the sum to be greater than 20,000. I want to know what's the least number of terms I add up to get this to be to be greater than 20,000. So I know I'm going to be taking first, it's arithmetic, going up by 4 each time, first plus last times n over 2. I want that to be 20,000. Now I doubt it's going to be exactly 20,000, but we want to find the first time when it is. It's probably going to come up with an n that's going to be a decimal, and then we would round up. Well, I got a problem. I have two unknowns here. But if I rewrite a sub n in its explicit form, there's this 5. Now I find the nth term by taking 5 and adding on 4 n minus 1 times. There's the last. First plus last times n over 2. And notice how many variables I have. I only have one, so I can solve it. I simplified inside here. I distributed. And now this, again, is doubtful that it's going to factor, but I would definitely go to quadratic formula with those numbers being so large. And calculated the quadratic formula and found out I get two answers. I get one that's negative, one that's positive. So I know I definitely need the negative one. And I got 99.25 for the positive value, which means 99 numbers is not going to be quite big enough to add up to 20,000. So I need to go up to 100. And again, I could go back and find what the 100th number was by taking 5 plus 4 times 99, and then take first plus last times n, which I'm saying I have 100 numbers, over 2, and double check and make sure it's just a little bit over 20,000. And it will be. So now you're ready to practice. Showed you a lot of examples of different ways that the arithmetic series can come up.